Thank you, Giovanni. Thank you. And thank you to the audience for still being here for this, my third presentation, that you're not sick and tired of me. Here, I want to talk about looking at urinary supersaturation from another perspective, and I've added to the title a proposal for a much simpler and obvious indicator of stone risk. So here's a quote from Finlayson from 1977, that supersaturation is really the most important factor, and indeed it's a widely regarded view, still true today. This quote is from 2011. It's the most comprehensive of all the numerous physicochemical risk factors that have been employed, and it's widely used as a diagnostic tool for stone risk. The advantages are that it's a holistic approach. It involves multiple urinary components synergistically working chemically with each other and takes into account multiple chemical equilibria. May I just briefly show you this chemical relationship? And I'm not concerned if you're a bit confused with this. The most important thing in this ratio is the Ca2 plus concentration. It refers not to the total amount of calcium, which is what we measure in the urine. It refers to the concentration of unbound calcium. It's just swimming around in the urine as Ca2 plus. That is one of the most crucial factors. So we're going to talk about that in a moment. So in a typical urine analysis, this is what we analyze for, and we get these values. But that's not really what we are interested in as far as the supersaturation is concerned, because in the urine are all these complexes that are shown next to the urine bottle. That is calcium that's bound in the urine solution to other chemicals. We're not interested in that in terms of working out what the supersaturation is. We're interested in the Ca2 plus, unbound, and the unbound oxalate and the unbound phosphate. And this is what helps us to determine the supersaturation. And in order to do this, there are various computer programs that allow you to calculate this. And this is widely practiced throughout the world, the calculation of the supersaturation of the urine. But keep in mind what it is that really determines the supersaturation. It's the unbound chemicals. So here is a typical result when one applies the supersaturation calculations. We find that it's significantly higher, the supersaturation, in recurrent stone formers. Here is a baseline urine model just arbitrarily taken, which I've used in order to do some modeling, some calculations using this as the baseline. And I'll come back to that and show you that in a moment. Now, the disadvantages of the urinary supersaturation as an indicator of stone risk, despite the fact of its popularity, is that a large number of urine input parameters must be measured beforehand. You must measure the total calcium, phosphate, citrate, magnesium. There's about 13 or 14 components. It's labor intensive and time intensive. It's expensive. The speciation software, not all of it, not all of them, but some of them, it's quite expensive, the licensing fee. And you do, in most cases, need a specialist operator, not in all cases, but the very powerful program, JESS, for example, requires a specialist operator. So that's a disadvantage. And the intervention target, that my understanding is, speaking to nephrologists and urologists, it's not reported in the literature, is that the supersaturation should be reduced by 50% in terms of the duration of the intervention. So what I don't particularly like about it, but it's fine, it seems to be arbitrary, but this does require you, of course, to know what the baseline supersaturation is, and then subsequently after that. So the question that this presentation is asking, is there a feasible alternative for getting the urinary supersaturation as a risk factor? It's widely used, very popular, but it's laborious. It has these disadvantages. Is there something else that we can do that's perhaps related to it? And of course, I spoke a moment ago, I showed you this is now a different diagram. This is the process of getting supersaturation. So here's the first point that I want to make. All of this is highly dependent on the pH. So the supersaturation is eventually depends on the pH. So here's a paper, urinary pH as a target in the management of lithiasis patients in real-world practice. So here is the proposal to use pH, which determines supersaturation, which is regarded as the indicator of stone risk. This is an alternative. So this paper tells us that less, and you've seen this a couple of times today, pH less than 5.5 is uric acid, pH greater than 6.2 is calcium crystallization, and that there's a preventative range, as it's called. I'm not so sure about that word, but I have had discussions with Rosenda about this. It's a range where the risk is lower, but anyway, that's a fine point. Where there is less probability, oh, there it is, or less risk to form stones. That's the preparation that is used, containing phytate, magnesium, and polyphenols. And as we heard earlier on today, there's a pH meter which is available for patients to use. So in the work that the group was done under, self-reported renal colic events decreased after the achievement of reaching this target. So recall that the pH ultimately determines the supersaturation, which is the risk factor. And here's some modeling that I spoke about. These are theoretical calculations of what we call the speciation. And along the y-axis, there's the supersaturation. What this shows is that for any value of calcium, that's the full calcium, and the oxalate, the full oxalate, the supersaturation decreases as the pH increases. Why? Well, here we show, again, this is from modeling, and I want you just to look at the green curve, which is showing, so I'm coming back now to the free calcium, which ultimately is what determines whether you're going to get calcium oxalate crystallization or not. And you see there the variation as a function of a pH. And as the pH increases, so the calcium ion concentration increases. And so here's my point, that the free unbound calcium, to me, is an alternative target to measure. Instead of going to the trouble of determining the supersaturation per se, you determine the calcium free ion calculation, which is dependent on the pH. So the problem with that, as I'm going to show that, I think this is about my last slide, the problem is that determining measuring the free calcium, because those programs calculate it, measuring it is technically difficult. So my proposal, DeviCare, listen to this, adapt your existing pH meter to accommodate a calcium ion selective electrode. That pH meter, the device that you have, is terrific. It's very, very user-friendly, very clever, very good engineering. So there it is. So it's got one electrode in that cup already for the pH. I'm proposing for home use a device for measuring the free calcium. Measure the pH, so here's the spin. Measure the pH and the free calcium simultaneously in the same urine sample and determine the stone risk. You've got two risk indicators that are closely related, the pH and the free calcium. Determine the stone risk. There's no urine analysis of multiple components that's required. There's no calculation of the supersaturation using complicated software. So the problem is it's technically difficult, but just do it. Thank you very much.